Hello everyone and welcome to today's lecture which is about imperfection in solid part 2. You remember that we started studying the imperfection in solids or in crystalline solids in last lecture, and we said that every single crystalline solid has imperfection, has deviation from its perfect structure, has defects in other words. And we categorized these defects into three main categories: point defects, line defects or dislocations, and surface defects. We already studied the point defects and we started studying the line defects, the introduction to dislocations, and in today's lecture we're going to continue with studying dislocations. Dislocation movement has an extremely important role in determining the plastic deformation in crystalline solid or in metals and alloys. This is because of what is called a slip of dislocation, and we're going to explain what is the slip of dislocation in this slide. First, we need to know what is a slip plane. The slip plane is the plane that contains both the dislocation line, which is here, this dislocation line, and Berger's vector. You know, Berger's vector is here, but it can transfer here. It can transmit it to be here because it is vector. So the only plane that contains both dislocation line and Berger's vector is this plane, and it's called the slip plane. Now let's propose that we have this crystal structure, this singular crystal, and in this singular crystal we've got one edge dislocation, one extra half a plane inserted here. What would happen if we apply a shear stress to this crystal structure? The most important, the most acceptable scenario and energetically favored scenario is that something has to happen around the dislocation, because the dislocation, having a dislocation in the crystal structure introduce a distortion to the structure. This area or this region here has more energy than others, and anything would happen, would occur, would start from here. So what's going to happen is under the effect of shear stress, this bonds between these atoms, this set of atoms here, and this set of atoms here will break. The bonds between these set of atoms and this set of atoms will break, and a new bonds between these atoms and these atoms will establish. Okay, so these sets of atoms break, and these sets of new sets of atoms will establish, leading to move the dislocation line from this position to this position. And under the continuous effect of shear stress, the bonds between these atoms and these atoms will break again, and another bonds will form or establish between these atoms and these atoms, and so on. If this process occurs, it will end with them kicking out the dislocation line out of the crystal, or changing the shape of the crystal from this shape to this shape. Those at the end of slipping, this process called slipping, dislocation slipping. dislocation, slipping, and at the end of each slipping event, the crystal shape will be different. It's obvious that the crystal shape here is different from the crystal shape here, and this is exactly the definition of the plastic deformation or permanent deformation. The final shape of the metal or alloy is different from the starting shape of metal and alloy. And by repeating this process many times, thousands of times, the shape of the metal and alloys change under the effect of sufficient shear stress or under the effect of sufficient stress in general. Slipping or dislocation movement, as explained in the last slide, occurs because it is energetically favored. It is the best way to respond to the applied stress. Let's propose that we've got a perfect crystal structure. Perfect. Ignore this line here, and let's start this perfect crystal structure. When we apply a shear stress on this crystal structure, and we need to change the shape of this crystal structure, what we need to do is breaking all the bonds between these atoms, all the bonds here. All the bonds here, which is 1, 2, 3, 4, 5, 6. 6 bonds. We need to break 6 bonds. 6 bonds times the number of the atoms in each layer, because this is a row. This is a layer of atoms, and this is a layer of atoms. So we need to break all these bonds to be able to move the upper portion of the crystal away from the lower portion of the crystal. Those having dislocation in metals and alloys makes this process much easier, less energy consumption. The energy consumption reduced significantly for plastic deformation by having, just because of dislocation, but just because of having dislocations, as explained in the last slide. Those having the dislocation is the main reason of, or the main mechanism of the plastic deformation in metals and alloys. Again, a simple comparison between the energy needed to break all these bonds and compared to energy needed to break just set of atoms and establish new atoms is quite clear. Quite clear. This also can be visualized from our daily life. For example, the caterpillar. The caterpillar, this lazy worm, this is very lazy worm, and when it needs to move, instead of moving all its legs, what it does, it moves the only portion, only small portion of its back legs here, making a kink, and then push the kink through her body to make the movement. Thus she creates a kink here, and there's a difference between this position and this position, by making a kink and then pushing the kink, and finally she moved itself by consuming much less energy than the movement by using all its legs. The kink here is quite similar to having dislocation. quite similar to having dislocation. And you remember this symbol is for dislocation. Another example is when we have a big carpet in a room and we need to reposition this big carpet. And instead of moving the whole carpet, we can make a kink and then move the kink to reposition the carpet. We mentioned that the dislocation movement or slipping process is crucial in determining the plastic deformation in crystalline solids. However, there are some preferred slip direction and the slip planes that the slipping occurs on. Before starting with this, I would like to define the slip system. The slip system is the combination of the slip plane plus the slip direction. The slip occurs on a plane at a particular direction. So the combination of a slip plane plus the slip direction called the slip system. First, we need to know what is the best slip direction that the slipping occurs on. And we can read this paragraph here. The stress required to cause the dislocation to move increasing exponentially with the length of the Berger's vector. Thus, the slip direction should have a small repeated distance or high linear density. The closed packet direction in metals and alloys satisfy this criterion and are the usual slip direction. What does that mean? That means the slip occurs preferentially on the high packet direction or on direction with high linear density. Let's take BCC as an example. For BCC, the direction 111 is the highest density direction, highest linear density direction, because it has these atoms on it. It is more dense than this direction, 101 direction, or this direction, 011 direction, or even this direction, 100. So this is because this is the highest density direction, the most dense direction. We expect the slipping occurs in this direction. In FCC, on the other hand, the most dense direction is the family of direction 110. This one, for example. Or this one, for example, the one started from the origin and ends here. The one started from the origin and ends here. The one started from the origin and ends here. Because these directions are the most dense direction with the highest linear density. For a plane, which is the preferred plane preferred plane for the slipping to occur on, it is also the most dense plane. We talked about the direction, and we said the most dense direction is the preferred direction for slipping. For planes, the most dense planes the most dense plane is the preferred plane for the slip to occur on. Thus, for BCC structure, the preferred plane is the most dense plane, which is that plane here, 110. Because the density of this, the planar density of this plane is the highest among all others. It is denser than this plane, denser than this plane, and denser than this plane, denser than all other planes. In FCC structure, the highest density, the highest planar density plane is 1, 1, 1, because it includes the most of the atoms in the crystal. It's denser than any other one, and you can check it by yourself. Double check it by yourself. So 111 plane is the most dense plane in FCC. Let's check this mathematically. Here we've got a question saying calculate the planar density of the 110 and 112 planes for BCC ion and interplanar spacing for both planes, on which plane slip would normally occur. The question is here, on which plane slip would normally occur? The lattice parameter of BCC ion is this, 0.2866 nanometer. So first we need to calculate the planar density. And you remember that calculating planar density from one of our previous lecture is the number of atoms in the plane divided by the area of the plane. And for BCC, for 110 plane in BCC, we've got two atoms, one in the middle and one quarter on each corner. So the total number of atoms is 2. And the area, we remember how to derive the area as a function of R, as a function of as a function of lattice parameter. So what we need to do is just putting the lattice parameter here, lattice parameter A. So the lattice parameter given in the problem in nanometer, we need to convert it to centimeter, because this planar density is normally measured by atoms per centimeter square. This gives us the planar density of 110 plane. In the same way, we can calculate the planar density for 112 plane, and it's here. The planar density of 110 is higher than the planar density of 112, and this gives us an indicator that slip would occur easily on this plane, on 110 plane. But we need to double check our results. And to do so, we need to calculate the interplanar density between the planes. Interplanar density can be calculated easily. Interplanar density D, interplanar spacing D, D for 110 is the lattice parameter divided by the square root of the summation of the squared indices of that plane. So the square indices of that plane is 1 square plus 1 square plus 0 square. Again, interplanar spacing for any set of planes equals for cubic, just for cubic unit cell, equals the lattice parameter divided by lattice parameter in centimeter, obviously, divided by the square root of the summation of the squared indices. And this gives us the interplanar spacing for 110, which is the spacing between each two successive planes, or the distance between one plane and the next one with the same indices. because you remember that planes with the same indices are parallel to each other. So here we calculated the interplanar spacing between them. In the same way, we can calculate the interplanar spacing for 112, and obviously the interplanar of 110 is higher than the interplanar, or they are more away from each other. Now, we do expect from our understanding, we do expect that the slip would easily to occur on the most dense planes, and this criterion is met here. This is more dense. The density is higher in comparison to the density of this one. And we do expect logically that the slip would easily to occur when the interspacing or the distance between one plane and the other is higher. And the criterion is met here. The criterion is met here. So both calculation, both determination of the interplanar spacing and the planar density gives us a clear indication that the slipping would much easily to occur on 110 plane in comparison to 112. In spite of the crucial importance of the dislocation in determining the plastic deformation in metals and alloys because of having metallic bonds, this is not always the case, or this is not correct in other kind of material, in other sort of material, like materials which are covalently bonded, like silicon. In these materials, the strength of the bond is higher than metallic bond, and these bonds are directional, is not non-directional like metallic bonds. And we remember the definition of directionality in bonding from our previous lectures. This leads to the fracture of like this material to be brittle fracture, not ductile fracture. Brittle fracture means that the material, after past elasticity limit, it exhibits very limited permanent deformation before fracture. While ductile fracture, which normally for metals and alloys, in these material, the material exhibits a long plastic deformation after elastic deformation, plastic deformation, or changing in the dimension, large amount of changing in the dimension before fracture. These material with covalent bonds exhibits brittle fracture. In the same way, dislocation does not play dislocation or dislocations in general. Dislocations do not play an important role in the deformation of polymer, because most polymer has a large portion of its volume with amorphous structure, and the concept of dislocation based on crystalline structure, so they are not important in polymer. Equally, for material with ionic bonding like many ceramics, titania, zirconia, MgO, all these material has ionic bonding. With these material, dislocations are not that important in deformation. because these material consist of positive ions, cations, and negative ions, anions, and moving the dislocation through these cations and anions will disrupt the electric arrangement of these material. Again, their dislocation are not important for covalently bonded material, for ionically bonded material. It is useful to repeat or to add some information to our knowledge in one slide, talking about the importance of dislocation and dislocation movement. First of all, as we mentioned before, the dislocations and the dislocation and having dislocations leads to metals to be exhibit high plastic deformation amount, or what's called ductility. The metals and alloys are ductile just because having dislocations. And without dislocation, as we mentioned in the last slide, the metal would need a lot of energy to be deformed. And it is calculated that the energy needed shown that the actual strength of metals, the strength of metals is 10 to 3 to 10 to 4 times lower than that expected from the strength of metallic bonds. Which means that if there is no dislocations in the structure of metals and alloys, and we need to deform these materials, we need to break them, break the metallic bonds, which means we need 10 to 3 to 10 to 4 higher strength, higher stress, higher applied stress to do so, which is quite high. Thus, the dislocation is the only reason, is one of the most important reasons actually, to have ductility in material, in metals and alloys. Also, same here, the ductility. We are talking about the ductility. Same here. First point and the second point talking about the same issue. Third, the mechanical property of the metal and alloys can be controlled by increasing or decreasing the number of these defects. As we will explain this in next lecture. Those, if we, but essentially, by increasing, just general overview, essentially, when we increase the number of dislocations, we strengthen the material. We increase the strength of material. By decreasing the number of dislocation, we increase the ductility of material or reduce the strength. Dislocation also influence the physical properties of material, of metals and alloys. For example, the electric and optical property of metals are significantly affected by number of dislocation. For example, the resistance of pure copper increases with increasing dislocation density. Is the length of let's talk about the dislocation density definition before go through the information here. Dislocation density is the length of dislocations per unit volume, we know that the dislocation, each single dislocation is an extra half a plane. So it has a length. And the total length of dislocation, or all dislocation, the total length, each dislocation has a length. The total length of all dislocations in a volume of material called dislocation length. And it is huge. It is really huge. For example, the total here, the dislocation density of 10 to 6 centimeter per centimeter cubic. We are talking about just centimeter cubic of material, of solid material. Centimeter cubic of material, 10 to 6 centimeter per centimeter cubic of material are typical for the soft metal. It is for soft metal. For the with densities up to 10 to 12 centimeter length per centimeter for each centimeter cubic of volume can be achieved by deforming the material. Here is very very nice example to give you a sense about the length of dislocation or the density of dislocations in metals and alloys. If the dislocation density is 3.86 times 10 to 10 centimeter per centimeter cubic, for a metal, the total length of dislocation is equal to the distance from Earth to Moon. Can you imagine that one centimeter cubic of a metal, deformed metal, has a total number of dislocation length equals to the distance between the Earth and the Moon? Impressive. Schmidt's law is used to compare the stress needed for the slip to occur. It can be used to compare the slip needed between two slip systems in the same crystal structure, or compare the slip system with a particular crystal structure with another. I mean by that, we can test different slip system planes and direction in the same crystal structure. For example, 111 with direction 111 with 101 with direction 101 in the same crystal structure, BCC or FCC or so on. Or we can compare the stress needed for the slip to occur on FCC in particular slip system with BCC with a particular slip system. Or in FCC, the easiest slip system, in the stress needed to form a slipping in the easiest way in BCC, and compare this with the easiest way to form a slipping in BCC structure. This is the idea of Schmidt's law. Schmidt's law happens when a tensile stress, for example, this one is a tensile axial force. An axial force is applied on a crystals on a single crystal material, like this cylinder. This cylinder is single crystal material, and a tensile force is applied here. The cross-section area of this single crystal is I naught. Thus, the force, the axial force causes stress, which is F over A naught. Now, we don't expect any slipping in horizontal plane or any slipping in vertical planes. That can be visualized by holding a stack of playing cards. Playing cards, hold a playing cards in your hand, a stack of playing cards, and press them. There is no slipping between the cards, among the cards. No slipping at all. Whatever the force that you apply, the cards will stick to each other. There is no slipping between them. There is no slipping among all the cards. If we put these cards on a table and vertically and push them, there is no slipping as well. So we don't expect any slipping in the horizontal planes and on the vertical planes. However, if we hold this stack of cards by our fingers and put them with an angle on a table and then push them, the cards will slip over each other. This is exactly the idea of slipping in planes in singular crystal. Those we do expect slipping to occur on any plane with an angle with the horizontal. For example, this plane. Let's say this is the direction of slipping. The angle between the direction of slipping and the axial force is called lambda. And the angle between the normal on the plane, the normal on the slip plane, and the axial force is called phi. Remember that phi plus lambda might equal 90 degree, but is not necessary to be equal 9 degree. That's because some slip direction is not on the same plane. Not on the same plane. The slip occurs in a direction, but the direction is not on the plane. It is deviated from the plane in different direction, as we have seen in the previous slides. Those alpha phi plus lambda possibly equal 90, but not necessary. Now, the force in this direction is called the resolved shear force, which is F cosine lambda. This is for F, and this is lambda. So Fr, which is shear force, shear resolved force, equals F cosine lambda. And the force in another direction is that one, is the normal. We're concerned about this. Yeah. So Fr, the shear resolved force, which is the force needed for the slip planes to slip over each other. This is the force needed. The force needed again. This is the force needed for the planes to slip over each other. Fr, shear resolved force, equals F, the axial force cosine lambda. Now, if we divide this equation by A, which is the area of the slip plane, the area of the slip plane, and you know it's obvious that A is A naught, which is the cross-section area of the cylinder, cosine divided by cosine phi. This is quite obvious from this triangle. Now, if we divided this equation by A, we will get what is called Schmidt's law. This is Schmidt's law. Here, for this term, Fr divided by A is obviously the shear resolved stress. Here, it is shear resolved stress. Fr over A is obvious shear resolved stress. And for the other term, F cosine lambda, divided by A naught over cosine lambda, cosine phi. So F over A naught is the stress, is the tensile stress. F over A naught is the tensile stress. And cosine phi goes up, so we will get shear resolved stress equals sigma tensile stress cosine phi cosine lambda. And this is Schmidt's law. Yeah, here we can see the Schmidt's. I have added this slide to your PDF just to show you, just for your information, about what happens when we apply tensile stress for a single crystal sample. As we mentioned in the last slide, the slipping occurs in any slip plane and direction, any slip system that is not horizontal or not vertical. Neither is neither horizontal nor vertical. Those in any angle with the horizontal. Any angle with the horizontal. Those in this sample, in this illustration, the axial force causes a slip in this direction. In real life, actually, there is a rotation of the slip plane. This is the simplest illustration for the slipping. But in real life, there is a rotation. There is a rotation tilting in the slip planes toward the slip direction. As you can see, the angle between this plane and the direction of load is higher than the angle of this one, for example. So there is a rotation, there is a tilting in the slip planes toward the direction of loading. This is like just to show you how the. Let's take an example to show how does Schmidt's law work. Now the example says a single crystal of an FCC metal, whatever it is oriented so that the 001 direction is parallel to the applied stress of 5,000 pound per square inch. Calculate the resolved shear stress acting on the plane 111 slip plane in 0, -1, 1, -101 and -110 directions. Which slip systems will become active first? Now we need to illustrate the question in the first step. The load is applied parallel to 001. This is 001 direction. This is 001 direction. The force is applied in this direction. And this is a single crystal FCC. The force applied in this direction. And then the force is 5,000 pound per square inch. And the plane targeted is 111 plane. This is 111 plane. And we asked about the possibility of a slip occurring in 3 directions. The first direction is 0, 0, -1, 1. 0 here, -1, 1. This one. The second one is -1, 0, 1. -1 in X, 0 in Y, 1 in X, so this direction. And the third one is -1 in X, -1 in X, and 1 in Z, 0 in 1 in Y, 0 in Z, so this direction. So the question is about the possibility of a slip occurring on this plane, 1, 1, 1 plane in 3 directions. This direction, this direction, this direction. If we applied a load in this direction. First of all, to apply Schmidt's law, we need both the both angles, phi and lambda. Phi we can find it directly, but the problem with lambda we need lambda we can find it directly, but the problem with phi. So we need to find phi out. Phi is the angle between the normal on the plane and the force. The force is in this direction, and the normal of the plane, let's say, start from the origin. Any normal of the plane on this plane, 1, 1, 1 direction, 1, 1, 1 plane in FCC or in cubic crystal has to start from the origin ends to this corner. So it's here. Now imagine this triangle, which starts from this corner, goes to this corner and ends here. This triangle, I represent this here. So this is the upper corner, and this is the middle here, the point here, and this is the lower corner. And proposing that it is because it's a cubic, so all the edges are equal to each other, so we can propose it as one. Now we need to find the length between the origin and here, and the center of this plane, from here to here. We remember that we can find the whole length of this line starting from here to here by using Pythagoras. So this is 1 square plus 1 square equals to the length of this squared. Or the length from here to here is the square root of 2. 1 square plus 1 square is 2, so the square root of 2. This is the square root of 2, the length from here to here. And because we are interested in this length from the origin to this point, which is exactly the half, so the distance from here to here is square root of 2 divided by 2. And by using this triangle, we can find the angle which is 54.73. Now, the load is vertical, and the angle we are looking for is between the load, between the applied load and the normal on the plane. This is the plane. This is the plane that we are interested in. The normal on this is normal on this, and this is normal on this. This angle is same as this angle. By this way, we can find the value of phi, which is 54.73. Now everything is set. The result shear stress for 5,000 pound per square inch, cosine 54 times 73, cosine lambda. Lambda is known for minus 101, this direction. The lambda is the angle between the force, the applied force, and the direction, which is obviously 45. Those cosine 45 is known, and we can find the dissolved shear stress. For minus 110, this direction, this direction is perpendicular to this direction. Thus the lambda is 90, and because the cosine of lambda is 0, the final result shear stress is 0. And the last direction, oh, sorry, it's not that one. The last direction is 0 minus 1. This direction. Sorry for that. It has to be it has to be 0, minus 1, 1, this direction, 0, minus 1, 1, and because the angle is 45, those tau or shears of stress is here, is none. Those, we've got two directions, this direction and this direction, active because the shears of stress is high. The shears of stress compared to third direction, which is 0. This one and this one will be active. And this is normal. This is logical. When we applied a load on this direction, we don't expect any slipping in this direction, any gliding in this direction. The only two direction we expect the gliding or the sliding occur on is these two directions, this direction and this direction. The illustration for the whole problem is here and here.